All right, so today we have Fabio Marino, who will tell us about Vacua, symmetries, and Higgsing of Chern-Simons matter theories. Take it away.
Thank you very much. Thank you for having me today and for giving me the opportunity to talk. And I'd like to present today some work I've been doing with Marcus about Chern-Simons matter theory and their moduli space of Vacua. So just as a first slide, let me explain what is the strategy, what is the problem, and what is the solution that we provide. The problem we want to address is the description for 3D Chern-Simons matter theories, both with n=4 enhancing supersymmetry and just n=3 supersymmetry. We want to describe global symmetries, the moduli space of Vacua, and the Higgsing pattern involved thereof. And the solution that we provide depends on whether we are n=4 or n=3, and depends on actually the value of the Chern-Simons level. Indeed, as we will see in the n=4 case, for the Chern-Simons level being 1, we will rely purely on SL2Z dualities to obtain everything we're interested in. And let me briefly mention that this is not the core part of the talk. This is just more like an inspirational part, which takes part from works which are already known and kind of systematically presented. But it's more to inspire for what's come next, because then if you go for Chern-Simons greater than 1 case, all of this strategy, which works nicely here, doesn't apply anymore. And so in order to study the moduli space of Vacua, what we propose is to obtain some magnetic quivers to describe the maximal branches. And we will see how the two things are connected. And finally, all of this technology also applies to the n=3 case, where you still have some maximal branches, and therefore you can still obtain some magnetic quivers. So the idea of the talk is to go step by step. After just a brief list of facts about Chern-Simons matter theories, I will start from building some examples in n=4 with Chern-Simons being 1. Then I will generalize it to the Chern-Simons greater than 1 case, where, as we said, we need magnetic quivers. And then we will go a little bit more crazy with n=3 theories with Lagrangian and non-Lagrangian setups. So let's just start from...
I have a question. When you have the
Sure.
Electric quivers in the Chern-Simons level =1 case, do you also have magnetic quivers? Like, do they have nice 3D mirrors?
I'm not sure I understood.
So
Sorry.
in the case of Chern-Simons level =1, you said
Yep.
that you can find some transformation so that you have a standard quiver. Did I get this right?
Yes.
Yeah. And here, do you also have a nice magnetic quiver, or is it just
Well,
in the bigger than 1?
You can find it, but you don't really need it, because your SL2Z dual already contains all the information that the two magnetic quivers would have. But potentially.
Okay. Because not every quiver is easy to do 3D mirror symmetry on. That's why I'm asking. Like, maybe this class, the electric quiver is better than the magnetic, but no. Oh, that's fine. Okay, thank you.
No worries. So yeah, okay, let's start with some basic facts about Chern-Simons matter theories. We start from a 3D n=4 gauge theory with some vector multiplet and some hypermultiplets, and we add a Chern-Simons vector multiplet in 3D n=2, a Chern-Simons action for the 3D n=2 vector multiplet. And on top of that, we also add some superpotential terms connecting basically the value of the Chern-Simons level to the trace of the adjoint square, where the adjoint is the adjoint in the n=4 vector multiplet. This superpotential term gives masses to the adjoint, which can therefore be integrated out. And that's the reason why all of this quiver will be represented in this n=2 notation, even if we are n=4. We will always have a pair of Carrels representing hypermultiplets. Gauge nodes will be circle in 3D n=2. And whenever there is an adjoint in the composing the n=4 vector multiplet, we will explicitly write it. Whenever instead there is a Chern-Simons level associated to a gauge group, we will just write it in blue, and the adjoint is not depicted because it's integrated out. These models are in general n=3 SUSY preserving, but they can be enhanced to n=4 if these Chern-Simons levels are alternating. Namely, they have the same absolute value, but alternating in sign. And they can be engineered in Type IIB by using D3 branes suspended between NS5 and 1, kappa 5 branes. In particular, if we want to look at n=4 enhanced brane setups, so as we said, we need alternating KIs. This means that we just have one type of 1, kappa 5 brane in our setup, which in this point can be seen as a rotated version of our D3 NS5 D5 setup. We will always write therefore quivers and brane setup with the same color coded convention, which is actually going to come to be explained more precisely in the next slide. But at this stage, I just wanted to emphasize that 1, kappa branes, here depicted as dashed lines, will always produce a Chern-Simons level on the sides of the bifundamentals that they generate. And whenever we have two 1, kappas close to each other, since we have a Chern-Simons level that adapts to 0 in the central nodes, we will actually have no Chern-Simons level, and the adjoint is still there because it's not integrated out.
What is a 105 brane? Which one? NS or D?
You're asking what does it mean?
1,0, yeah, is this an NS5?
Yeah.
Okay, I see.
Yeah, all of these, how can I say, brainy conventions will be explained in a second.
Oh, okay,
sorry. No, it's right. And these models in 3D n=4 still enjoy an IR symmetry, which is SU2 times SU2. We cannot call these factors actually Coulomb and Higgs because these branches are mixed in the sense that the operators that describe them are not purely monopole or purely mesons, but since we have Chern-Simons, the monopole acquire non-trivial gauge charges, and therefore to be made gauge invariant need to be dressed with matter. But also this is going to be clearer when we look at the dualities involved in at least in the Chern-Simons =1 case. So as promised, these are the conventions that I will be using. So whenever there is a D3 suspended between NS5, I will have a n=4 vector multiplet written in the n=2 notation. Whenever there is a D3 suspended between NS5 and 1, kappa, or vice versa, we will have an n=2 vector multiplet, so no adjoint, and a Chern-Simons level, which is respectively plus or minus kappa. And then we have a bifundamental hypermultiplet whenever we have a string stretched across NS5, or a twisted hypermultiplet if we have a string stretched across a D5, a 1, kappa 5 brane, and fundamental matter whenever we connect strings between D5s and D3s. So let's now, with this machinery, try to build some setups in 3D n=4 with Chern-Simons being 1. But before starting, as I said at the beginning, we want to address this specific section through SL2Z dualities. So let me first review what we need for this. We consider the two basic elements of SL2Z, so S and T, which satisfy these properties here. And out of them, we can actually build another generator, T transpose, which is just a combination of S and T in this fashion. And we can understand the action of these dualities on our branes by using the PQ 5 brane notation. So if we write branes as vectors where NS5 is 1, 0 and D5 is 0, 1, then the action of S, T, and T transpose can be understood as this matrix multiplication. And in particular, among those, what we are interested in the most for the time being is T transpose. Indeed, if we take the branes that constitute our Chern-Simons matter theories, which are Simons being 1, namely NS5 branes, always depicted in red, and 1, 1 branes, because now kappa is 1, always depicted in blue. The action of T transpose is basically to send the NS5 brane into NS5 brane and the 1, 1 brane into 0, 1, so a D5. This basically means that our Chern-Simons matter theory built out of these branes is T transpose dualized into a standard T sigma SUN theory. And another thing which is mapped across T transpose is the Anani-Witten transition. Indeed, on the T sigma side, we know that when a D5 is pushed across a D5, there is the very famous Anani-Witten effect, which creates this setup here. So we need something which is the T transpose dual of this transition, which is known as the Given-Kutuzov. Here in particular, we are dealing with 1,1 5 branes. So what is the statement of the Given-Kutuzov dualization is that if you push a 1,1 through an NS5, what you get is this final configuration here. So let me now spell out what is the strategy that we will follow in this first section. We start from a Chern-Simons matter theory with Chern-Simons being 1, and we want to study all of these features. What we do is to T-transpose dualize it into something here called Q, which is a pure sigma, which will have a Coulomb and a Higgs branch, which are mapped to the 2 maximal branches of the Chern-Simons matter theory, which we will call A and B. Again, we cannot call them Coulomb and Higgs because they are not purely mesonic or purely monopole. And for this section, this first part of the diagram is more than enough. There is nothing else to be done. So what is the reason why I actually enlarge this this diagram? Well, it's just for symmetry, let's say symmetry reason with respect with what will come in the Chern-Simons criterion 1 section. So let me just briefly comment about this diagram. Suppose you start from this theory. Okay, we know how to get this T-transpose dual, but now suppose that you want to start from this Chern-Simons theory and obtain another Chern-Simons matter theory whose 2 branches are swapped. You obtain this result by T dualizing it, where T is the operator of SL2Z, and so you get another Chern-Simons matter theory whose 2 branches can be mapped into Coulomb and Higgs branches of a standard sigma via a T transpose to the power of -1 transformation. And finally, to close this diagram, what you need is to send this sigma into this other sigma with the 2 branches swapped, and this is nothing else but S. What is kind of important to notice at this stage is that this Coulomb branch is mapped into the A branch of this Chern-Simons matter theory, which because of this swap is mapped into the B branch of the starting theory. So in a sense, if we want to describe the 2 branches of the Chern-Simons matter theory, it would be enough to look at this Coulomb branch here and this Coulomb branch here. And this, at this stage, is not useful, but it's going to be the logic behind the magnetic quivers in the following section. But okay, for the time being, let's focus on this first part of the diagram, and let's just T-transpose dualize our theories. We start from a simple abelian example, 6 nodes, alternating Chern-Simons levels, where again, the color coding tells you what are the branes realizing which parts of the quiver. And the T-transpose dual of this theory is this sigma here. But what you can also do is to take this guy, Given-Kutuzov dualize it into something which looks like this. So you have basically dragged this 1,1 inside to obtain this theory here. And if you do T-transpose, you immediately get this theory without even the need to apply Hanani-Witten, because it's already applied on the other side of the duality. As you can see, there is a precise mapping between the fugacities of the topological symmetries on the Chern-Simons matter side and the topological and flavor fugacities on the sigma side. And this precise mapping, which is going to be crucial in the following analysis, is due to the dualization algorithm, which we use to implement this T-transpose dualization locally directly on the field theory. So what we can do now is to look, to stare at our sigma, rid of the global symmetry, which is the one written here for the Coulomb and Higgs branch. And then immediately we know that since it's a dual, we can write the global symmetry of the Chern-Simons matter theory. When, for convention, we decide that we call A the branch which is mapped into the Coulomb branch, and B the branch which is mapped into the Higgs branch. Moreover, through the parameterization that we have discussed, we can write the superconformal index for the 2 sides of the duality, match it, of course, where there is a reparameterization between these fugacities of the global symmetries, which are those used in the index here, and the fugacities written in the quiver. But that's not the end of the story, because we also are able to precise map all the operators across the duality. I mean, up to a certain order where we decide to stop. And this huge table, I don't want to comment too much about it. I just wanted to showcase, first of all, that one can do this mapping. but also that there is an interesting phenomenon, which, as you can see here, tells you that you can map the mesons of this sigma into dressed monopoles in the Chern-Simons matter site. In this case, you are creating an adjoint of SU2. Or vice versa, you can map monopoles into dressed mesons in the, in dressed monopoles in the Chern-Simons matter site. So this should make clear why we cannot really call Coulomb and Higgs branches the maximal branches of the Chern-Simons matter theories. They are mixed. So what have we done so far was to take a Chern-Simons matter theory and detranspose dualize it into a sigma. And we have said that we map the sigma Coulomb and Higgs branches into the A and B branches of the Chern-Simons matter theory. But we have also seen that the branes realizing the Chern-Simons matter theory, the 1,0 and the 1,1, are T-transpose dualized into NS5 and D5. So in the very same way that we usually say that the Coulomb branch is parameterized by the moduli of D3 stretched between NS5 and the Higgs branch is the moduli of D3 moving in intervals of D5s, we can say the very same thing for the Chern-Simons matter side. So the A branch is the moduli of the 3 segments between NS5 branes, and the B branch is the moduli of the 3 segments stretched between 1,15 branes. So this also generalizes, as we will see, to cases where the Chern-Simons is bigger than 1 and to PQ5 branes. And it also gives us an hint on how to do the Higgsing on these Chern-Simons matter sides. We have actually a few possibilities. We know how to map the operators, so we can take operators VEVs, or we can do this brane Higgsing because we now know what are the branes realizing the 2 branches. Or we can use very conveniently the Quiver algorithms, so decay and fission or Quiver subtraction, to do the Higgsing on the T sigma side and then dualize back every single part of the diagram. So let's see how does this thing work. We start from the Coulomb branch Higgsing of the sigma side, and we write its Hasse diagram like this. And then to read off the Hasse diagram of the A branch of the Chern-Simons matter side, we just dualize back through T transpose inverse all of these single theories, and we obtain the Hasse diagram of the Chern-Simons matter theory. Moreover, thanks to the operators mapping, we can also say precisely what are the operators taking a VEV in a specific transition. So here, for example, as I advertised a few slides ago, we have a monopole in the sigma side, which is taking a VEV, while here we have a dressed monopole, which is taking a VEV, and same here above. And all of this, of course, applies also to the B branch Higgsing. So we take, again, our sigma, we do the Higgs branch Higgsing, producing this Hasse diagram, and then we dualize back each layer of this Hasse diagram into the Chern-Simons matter side. And again, we can map the operators which are taking a VEV. In this case, mesons, which are mapped into, in this case, pure monopoles. But we can go a little bit more complicated than that. I don't want to go too much into the details, but just to showcase that it's a very generic recipe. Here it's a non-abelian 8 nodes theory, both in its starting setup and its given Kutazov dual. The T transpose dual theory looks like this. So you basically dualize these 1,1s into D5s, and the NS5 are untouched. Again, you can read off the global symmetry algebra from here, and it's going to be automatically the global symmetry algebra of the Chern-Simons matter side. You can match the superconformal index and the operators, and you can do the A and B branch Higgsing for the Chern-Simons matter theory. This is what I want to show now, and don't be overwhelmed by the slide. I'm not going into the details of this Hasse diagram. I just wanted to showcase this, that it's something that it can be done. So you take the Coulomb branch Higgsing of the sigma, you spell out what is the Hasse diagram, and you dualize back each one of these layers, and obtain the Hasse diagram for the A branch Higgsing of the Chern-Simons matter theory. And again, you can map operators. For example, here you have a nice symmetry enhancement on this side, which maps precisely into this symmetry enhancement on the Chern-Simons matter side with this beautifully dressed operator. And same story for the Higgs branch Higgsing, which you can write for the T sigma side. You go on the other side, you get the B branch Higgsing, and again, you can map operators. So just as a take-home message for this first section, we learned that we can understand everything about the modular space of Chern-Simons matter theories with Chern-Simons 1, thanks to the T-transpose dualization, which sends Chern-Simons matter into T sigmas, A branch into Coulomb branch, and B branch into Higgs branch. We have seen that we can match superconformal index and operators, that we can perform the A and B branches Higgsing via the Coulomb and Higgs branch Higgsing of the dual sides. And even though I am not making examples now, as you can imagine, all of these generalizes quite immediately to the circular case. You just put your setup on a circle, and everything works the same with the same dualization. The only difference is that here you won't have exactly a T sigma, you will have a circular version of it. So now the question is, what about Chern-Simons greater than 1? Well, one might be tempted to say, okay, maybe you just need to find a different SL2Z transformation, which sends your Chern-Simons matter theory with Chern-Simons greater than 1 into a T sigma. But this turned out not to be possible. For 3D n equals 4 Chern-Simons matter theories with Chern-Simons level greater than 1, there is no Lagrangian non-Chern-Simons SL2Z dual. In other words, you cannot find a transformation in SL2Z which maps 1, 0 into 1, 0 and 1, kappa with kappa greater than 1 into 0, 1, up to any choice of sign. To convince you about that, you just need to solve a simple linear system. So what comes out of this statement is you would be very tempted to write something like this, to map Chern-Simons matter theory into a T sigma through SL2Z, but this is simply not possible. So, okay, one is maybe a little bit sad at this point, but luckily enough, not everything is lost, because we can still capture the geometry of the maximal branches of the Chern-Simons matter theory with two magnetic quivers. We will call them MQA and then MQB, and their Coulomb branches will reproduce exactly the A and B branches of the Chern-Simons matter theory, which are Chern-Simons greater than 1. So how do you obtain such a magnetic quivers? Well, I will now go through the prescription, which might be a little bit awkward at the beginning, but hopefully it will become clearer and clearer after the many examples that I will present. So the prescription is the following. We have two branches and therefore two magnetic quivers. And the first one, which we call MQA, is obtained by focusing on the D5 charge of the 1, kappa bound state. So in particular on the second entry. And then is obtained by isolating the A moduli of the D3s suspended between S and S5 branes. So what does it mean from a practical point of view? It means that many quotation marks, you replace 1, kappa 5 branes with a set of kappa D5s connected to as many D3s as possible. And again, don't be scared. I will go to many examples in the next slides. But how about MQB instead? Well, one first swap the A and B branches via a T to the power of kappa transformation, where kappa is the Chern-Simons level, and then repeat this analysis here. So focus on the D5 charge of the 1, kappa and isolate the A moduli of the 3s.
Is it really a necessary step to do the swapping in this, or could you just suspend differently and then read again?
No, it's definitely necessary. And
okay.
It's probably going to be slightly clearer with this slide here. This really resembles what was the strategy that I proposed for Chern-Simons equal to 1. The only difference is that we don't have dualities anymore. We have these wiggled lines, which are basically the rid-off magnetic quiver operation. And the strategy is the following. This is the Chern-Simons matter theory you want to study, which has two maximal branches. And we claim that one of the two branches, the A branch, can be studied via a magnetic quiver A, whose Coulomb branch reproduces this A branch here. How about the B branch instead? Well, you first trade this B branch for the A branch of a dual Chern-Simons matter theory via this T to the power of kappa transformation. And then once you read off the magnetic quiver in the same way you did here, you obtain a magnetic quiver whose Coulomb branch maps into the A branch, just as it was here. But now the A branch of this theory is nothing else but the B branch of the starting one. So via this operation, you obtain two magnetic quivers, which can be read off in a fairly similar way. And you are describing the two maximal branches of the theory.
So maybe this will become clear when you do an example, but in the brane system, you see both the A and the B branch, right? Without doing any SL to Z.
Yep.
So then if you go to the B branch in the brane system, can you not then derive rules to read magnetic quiver directly from this without doing any transformation? Like,
well, if you think about it, what is changing here with respect to the Chern-Simons being equal to 1 case is only the D5 charge, not the other one. So it wouldn't make any difference to focus on the NF5 charge. It wouldn't make any difference between the Chern-Simons greater than 1 case and the Chern-Simons equal to 1 case. The only thing which is changing is the D5 charge. So somehow you always have to focus on this one.
Also, are the kappas different kappas?
Where?
In one quiver, can you vary kappa?
No, if you want to stay n equals 4, it has to be always the same kappa up to signs, and then you will have alternating Chern-Simons levels. If you allow for different kappas, you break to n equals 3, and this will come actually in the final part of the talk. It's also possible to do that for that setup. Is just slightly more involved.
Okay, I'll just let you continue. I'll ask more later.
No I'm happy to reply. Sure. So okay, this is the strategy. Let's now make it more concrete with some examples. Let's start from a theory with 4 nodes, non-abelian, with a generic Chern-Simons level plus or minus kappa, realized by this brane setup here. The first magnetic quiver for the A branch is read off immediately by, again, focusing on the D5 charge here. So we replace this kappa with kappa D5s. And this is the magnetic quiver that we read off. And to read off instead the other magnetic quiver, we first swap the 2 branches. So we swap NS5 and 1 kappa via this T to the power of kappa transformation. So we get 1 minus kappa and NS5, where this sign is not really relevant because we are taking the absolute value of the D5 charge. Then we read off the magnetic quiver here, and I will explain the details in a second. And we obtain this maximal, this MQB, which describes the A branch of this theory, which is the B branch of the starting one. So these are the 2 magnetic quivers describing the 2 maximal branches of the starting theory. Now let me just explain how did I obtain this guy here. Let's start off from this brane setup, which is reported here. We have 2 possible ways. First one is to replace all of these 1 kappa straight away with kappa D5s, and this is what we get. And then we bring as many as we can in the NS5 interval, and so we get kappa plus 2n flavors. Or we first apply a given quotas of dualization. So we push this 1 kappa through the NS5, creating kappa D3s, where this is the generalization of given quotas of 2 higher values of D5 charge. Then we substitute this 1 kappa with kappa D5s, and we push away as many D5s as we can, reaching the same magnetic quiver configuration, which is indeed the one I wrote here. So there is one more thing I wanted to comment about, which is the goodness of the starting theory. The goodness of this of the Chern-Simons matter theory is ensured if the 2 magnetic quivers are both good at the same time, meaning that there are no operators in the 2 maximal branchings falling below the unitarity bound. And then we can just take the strongest goodness condition on these 2 magnetic quivers to be the goodness condition on this Chern-Simons matter theory. And you can convince yourself of this fact by just checking the index of this theory and plugging in values which are not satisfying this goodness condition. You will find theories which are indeed bad. So this can be taken as our goodness condition. And from our 2 magnetic quivers, we can now do the analysis that we were doing before. So you read off the global symmetry algebra, which depends on the value of kappa with respect to n. Indeed, if kappa is equal to n, we have an enhanced global symmetry on the A branch, so in MQA. And at this point, what you can do is not to match the index anymore, but what you can do is to match the Hilbert series. So you know how to obtain the Hilbert series on the Coulomb branch on the magnetic quivers, but to obtain it on the Chern-Simons matter side, what you can do is to do something very analogous to the usual index projection on the maximal branches. So you take your index, which is at the beginning dependent on two fugacities, which are symmetry and the axial charge. And then you redefine this x and t in terms of two other fugacities, here called A and B, which captures the information about A and B branches respectively. And then if you want the Hilbert series on the A branch, you just turn off B, and vice versa. And if you want the Hilbert series on the B branch, you just turn off A. In this way, you obtain the two Hilbert series, the Hilbert series for the two maximal branches of the Chern-Simons matter theories, which can then be matched with the Hilbert series on the Coulomb branch of the two magnetic quivers. And at this point, what is left to do in our schedule is to do the A and B branch Higgsing, which can be done by, for example, taking kappa equal to n, can be done by just doing the Coulomb branch Higgsing on the two magnetic quivers. Here in particular, I have NQA, and I'm now doing the Coulomb branch Higgsing. So I remove the three segments between NS5s. In this first step, I have an enhanced symmetry, so I can remove the long one. In the following step, I don't anymore, so I just remove the shorter ones. And these manipulations here are mapped precisely in the Chern-Simons matter side by removing long D3 segments at the beginning because we have an enhanced symmetry, and then it's just shorter ones, creating this Hasse diagram here, which indeed reduces to just the structure here if kappa is just greater than n, so we don't have the starting symmetry enhancement anymore. On the other hand, if you want to obtain the B branch Higgsing, you take magnetic quiver B and you do the Coulomb branch Higgsing, just removing these D3 segments. And this maps back into the Chern-Simons matter side, where to be more clear, at the beginning, I first pushed away these 1, kappa 5 branes, because later, when I start doing the Higgsing, I want to remove the long D3 segments, just to match precisely with what I'm doing with the magnetic quiver here. So, so far we have seen how linear trained inequals for Chern-Simons matter theory, when it has Chern-Simons greater than 1, can be described via two magnetic quivers, but this actually can be generalized to circular quivers. So instead of making more examples in the linear case, let me just make some more examples in the circular case where everything works in the same way. But it's actually nice because we can not only reproduce some results present in the literature, but also go beyond. Let's look, for example, at this very symmetric example where the two branches are isomorphic, since we have alternating NS5 and 1, kappas. How does it work? Again, 1, kappa is, if we want to read off the magnetic quiver A, we replace 1, kappa with kappa D5s, and we read off this magnetic quiver here. If we want to read off instead magnetic quiver B, we first swap NS5 and 1, kappa via T to the power of kappa. But this swap is nothing else but by rotating a little bit this brane setup, and therefore the magnetic quiver that we read off is exactly the same. A less symmetric example is this one. So take a circle with 1 NS5 and L 1, kappas. If you want to read off MQA, you substitute this 1, kappa with kappa D5s. So you get L times kappa flavors and one adjoint hypermultiplet. While instead, if you want to read off MQB, what you can do is to first swap NS5 and 1, kappa. So you get L NS5s here, which are here. And then you get 1, kappa, which then to read off MQB is turned into kappa D5s. And so we have this structure here. So what did we learn so far for the Chern-Simons matter theories with Chern-Simons greater than 1? We cannot rely on SL2Z dualities anymore, but we can still analyze the maximal branches via a magnetic quiver prescription, which is basically of replacing 1, kappa bound states with kappa D5s, or to read off the A branch, or to read off the B branch, first swap NS5 and 1, kappa, and then repeat the procedure. We have also seen that all of this allows you to precisely spell out what are the Hasse diagram for the A and B branch Higgsings. And also it generalizes to circular quivers. Let me now go a little bit more crazy and go for n equals 3, which means that, at least in the Lagrangian case, means that we are allowing for various 1, kappas. So this breaks down SUSY to n equals 3, but we still have many maximal branches. Actually, we have a maximal branch for each type of distinct 5 brane. So our magnetic quiver prescription still applies, but we will have, instead of 2 MQA and MQB, we will have as many magnetic quivers, as many maximal branches we have. So don't be overwhelmed by the upcoming figure, but our strategy is here depicted. Again, it might be a little bit overwhelming at the beginning, but it's actually quite straightforward. You start from a Chern-Simons matter theory, which has many types of 5 branes. So it has NS5 branes, D5 branes, 1, kappa 1, 1, kappa 2, and so on and so forth. And you want to analyze all of these branches, which are now called branch NS5, branch D5, just because we have many of them. So the branch NS5 is what we previously used to call a branch, and we can immediately construct a magnetic quiver for it just by replacing all the 1, kappas into kappa D5s, and we read off a first magnetic quiver. Then suppose we want to study the 1, kappa 1 branch. We first need to swap 1, kappa 1 with NS5, which is done by t to the power of kappa 1. And you obtain a Chern-Simons matter theory whose NS5 branches are what it used to be 1, kappa before. So if we now read off the magnetic quiver for this NS5 branch, we are actually reading off the magnetic quiver for the 1, kappa 1 branch of the starting theory. And again, suppose you want to go for the branch 1, kappa 2, you swap 1, kappa 2 with NS5 with a transformation which is t to the power of kappa 2, and you obtain a Chern-Simons matter theory whose NS5 branch is nothing else but the 1, kappa 2 branch of the starting theory. And so you apply this technique over and over until you have analyzed all of your D5 branches, all of your 1, kappa branches, and then you are left just with D5, which to be analyzed, you need to swap with D5. And this is just done by implementing an S transformation. So you obtain a Chern-Simons matter theory whose NS5 branch is the original D5 branch. So once you read off its magnetic quiver, it's actually going to be the D5 magnetic quiver of the starting Chern-Simons matter theory. I know that this was a lot of words, but hopefully with the next examples, it's going to be clear. Let's start with a abelian 3-node case where we have 3 branches. So we have the branch related to NS5s, the branch related to 1, kappa, and the branch related to D5s. So basically, what we would need to fully analyze this theory is a set of 3 magnetic quivers. And this is how it works. Let's start from the NS5 branch. We have this brane setup. We focus on the D5 charge, and we substitute all of the 1, kappas with kappa D5s. So we have 1 D5 here, kappa D5 coming from here, 1 from here, and kappa from here. Then you bring as many D5s as you can inside the NS5 interval, which is just 1 because you have only 1 D3, and you get kappa plus 2 flavors. So this is the first magnetic quiver for the NS5 branch of this Chern-Simons matter theory with n equals to 3. Suppose now you want to study instead the 1, kappa branch. You just need to substitute NS5 to dualize NS5 into 1, kappa and vice versa. And to do that, you need t to the power of kappa, which sends NS5 into 1, kappa, D5 into D5, and 1, kappa into NS5. Again, you read off the magnetic quiver by substituting kappa with kappa D5s, and you get 1 here, kappa, and 1 coming from the outside. So kappa plus 2 again. And this is the second magnetic quiver. Finally, to read off the magnetic quiver for the D5 branch, you just need to swap NS5 and D5, and you do that by S duality. So NS5 goes into D5, D5 goes into NS5, and 1, kappa goes into kappa, -1. Again, you focus on the D5 charge, which is just 1 here because we are focusing on the second entry. one from here, and one from here, which goes inside. So 4 in total. So this set of 3 magnetic quivers describe the 3 branches of this theory, and indeed it matches with what was known already in the literature. But we can go beyond the literature and go non-abelian. So we take the same theory, but we put instead n d3s and fully flavor it. Again, we have 3 types of 5 branes, so 3 maximal branches. And let's see how does it work. Again, to read off the magnetic quiver for NS5, we just straight away send this 1, kappa into kappa d5s, and same here. So you have F1 d5s from here, F2 from here, kappa from here, and n coming from the outside, because we are assuming just for convenience that F is greater than n. So we have this number of flavors. And that's the first magnetic quiver. Then suppose you want to read off the 1, kappa branch. Then you send NS5 into 1, kappa, D5 is sent to NS5 to D5, and 1, kappa is sent to D5 to NS5. And then again, you read off the D5 charge, and you bring as many D5s as you can inside, and you read off F2 plus kappa plus F3 plus n coming from the outside, and that's the number of flavors that you have here. And finally, for the D5 brane, for the D5 branch, you just dualize NS5 into D5 through S, and this creates a stack of NS5 corresponding to this stack of D5s. And then you need to push this D5 as far as you can, which creates this plateau in the magnetic quiver, or this plateau on the other side, because here you have again one D5 charge, and then you have this flavor in the middle of the magnetic quiver. So it's actually, I mean, this magnetic quiver is quite massive, but still in a very straightforward way, you have found three magnetic quivers describing the maximal branches of this n equals 3 Lagrangian Chern-Simons matter theory. But once more, we can be more crazy than that and go non-Lagrangian. So instead of allowing for 1, kappa, we can allow for P, Q 5 branes, which indeed create a non-Lagrangian theory, which can be described through J-folds, but which still has and as many maximal branches as many types of PQ5 branes that we have. And therefore, again, our strategy still applies. We will have one magnetic quiver for each maximal branch. So the picture that we have with respect to before is exactly the same. So we have this transformation, which allows us to go to Chern-Simons matter theory, whose NS5 branch is nothing else but the PQ branch we're starting from. But this transformation at this stage will not be anymore just T to the power of kappa in SL to Z, but will be some SL to Z transformation, which can be anything in the second column, as far as the first column is P, Q, where the P and Q are those that you are looking for. And the reason why you don't care about the second column is that you are only focusing on the D5 charge, so on the second entry of the bound state. So again, this strategy is the same as before. Let's put it at work in a couple of examples. So we take the same abelian theory we had before, but instead of having 1, kappa, we take P, Q. And we don't write the quiver because it's non-Lagrangian, but still we can analyze the maximal branches. So same story as before. You have this P, Q, you turn it into Q D5s, and you have one D5 coming from here, Q from here, and one from the outside, which can be brought inside, and you get Q plus 2. Then you want to read off the P, Q branch. So you trade NS5 for P, Q with this transformation, which maps NS5 into something, Q. That's something we don't care. Maps D5 into something, P, and again, this something we don't care. And then PQ into NS5. Then, same story as usual, we read off the charge of D5, which turns out to be P plus Q plus 1 coming from the outside, which is here. And finally, to read off the D5 charge, swap D5 with NS5, and what you get is this setup here. So you read off, again, the D5 charge, and you have 1 plus P from the inside plus 1 from the outside, so P plus 3. And again, this reproduces the results available in the literature. But again, you can be more brave than that and go for non-abelian. So you put, it's the same theory as before, you put now ND3s, fully flavored, and PQs, and you again have 3 maximal branches, which are described by 3 magnetic quivers, which are obtained again in the same way. You just read off the d5 charge from here, which is Q plus F1 plus F2 plus N from the outside, which is this. You do this SL2Z transformation and you map your system into the same thing we had before, but now you have stacks of these sampling, P branes. You read off the d5 charge, which is F3 times P plus Q plus F2 times P plus N coming from the outside, which is this guy. And then you map this guy through S into a brane setup which has D5 and NS5 brane swapped to read off the D5 brace, the D5 branch. And again, you have stacks of NS5s, and here you have PD5s. So actually, the result of your magnetic quiver depends on the value of N with respect to P. But as soon as you fix it, your magnetic quiver is fixed, and you have again obtained a collection of 3 magnetic quivers for your maximal branches. So let me, after this huge amount of example, let me finally jump to the conclusions. We have analyzed the moduli space of 3D n equals 4 linear and circular Chern-Simons matrix theories. And we have seen that as soon as the Chern-Simons is equal to 1, everything is fixed, is analyzable through SL2Z dualizations. While instead, when the Chern-Simons level is bigger than 1, we need to obtain 2 magnetic quivers for the maximal branches, which still allow for all the analysis we're interested in. We have also seen that this extends to 3D n equals 3 Chern-Simons matrix theories, both in the Lagrangian and in the non-Lagrangian case. And finally, let me also mention that all of this opens the door to some further analysis, like the inclusion of orientifolds in these brane setups, and also the interplay with of I-form symmetries with this magnetic quiver prescription. So thank you very much for your attention.
All right, let's thank Fabio. Do we have questions? So what you're saying with is that for like J-folds and these like higher Chern-Simons theories, like everything is basically just as easy as for a 3D n equals 4 theory to like a Chern-Simons less 3D n equals 4 theory. It's just that you have to maybe iterate the same thing a few more times and you have to check the rules. But like, this is really nice. That's very cool. And so my comment of earlier, I would say that in the brane system, like you don't have to do any dualizations, but in one brane system, you can do all of the different maximal branches, and then you just adjust your rules and you read like a magnetic quiver for each thing. Like you don't read, like there is nothing physical happening in the transformation. It's the information there and it's contained, and you can also do all the maximal suspension. You have to be careful, maybe using the S rule properly, but otherwise, like it's a.
I mean, probably you can. I think that's this kind of operation of swapping the branches and looking always for the same magnetic quiver makes a lot of sense from the prescription point of view, because we are always focusing on the same kind of moduli, which we already know how to focus on. Yeah, exactly.
And so if you compute the Higgs branch of your magnetic quivers, is there any information in there that like tells you something about your theory?
I mean,
like
not that I noticed.
Okay.
Maybe there is, but it's very hidden. I don't know, but if you look at it, it's just something completely different, but the Coulomb branch is instead precisely the same.
Yeah. I guess if you're writing a magnetic quiver, like, of course, this is not really truly associated to your phase in your brane system, because you're kind of forgetting that certain branes also have an S charge, and you just pretend they just have D charge and so on. So it's like it's cheating a little bit. So I guess
exactly.
Sorry, maybe an extension to Julia's question. So if you have 2 n equal to 3 theory, but you will get 2 magnetic quivers at some sense, so did you find in some cases, like if they are the magnetic quiver are mirror due to each other, so can you make some any claim on the n equal to 3 series? Is there any connection?
You mean a duality between the magnetic quivers?
Yes. So if you
I think that if this happens, it's very very fortunate. I don't see a reason why there should be a duality connection between the two magnetic quivers in general.
I see. So it's like some hidden information you cannot see from -3.
You mean if it happens, if it's providing some
if it
information?
happens. Yeah.
No, I would just say it's an accident.
Mhm.
Because again, you're really, as Julius said, you're kind of cheating. You're just focusing on a specific part of the bound state. So
Yes.
if there is a duality in these magnetic quivers, I guess it's just an accident. Yeah.
Thank you.
No worries.
Or maybe it could indicate that really you do have like secretly no Chern-Simons or something if you have such a duality.
Well, if you put a Chern-Simons level equal to 1, if you read off the magnetic quiver in this way, then
it
they are
also
dual,
happens
but
in other cases where you have these two, like where you have magnetic quivers which are like, for example, if you have two branches and the two branches the quivers are 3D mirror, could you have this thing and your original theory cannot be dualized to one free of Chern-Simons? Like can this happen?
say it again.
So if you have a Chern-Simons matter theory where you have, or I don't know what the right word is, but anyway, you have a theory where you have just two branches, so two types of branes, and now the two magnetic quivers are 3D mirror of each other. Then I would guess that the original theory actually has some frame where it's just some vanilla 3D English 4 theory. No. Because well, at least the moduli spaces are now just that of one. Maybe there's some extra data which prevents it from being that.
Yeah, it might be, but I honestly never found such an accident, so I wouldn't know how to check such a conjecture.
Okay. Do we have more questions for Fabio? In that case, I would say let's thank him again. And we can go off the record.